Today we'll do our last section in this very brief preparation for series unit on improper integrals. So what we have done so far when we have been doing definite integrals, our limits of integration were always some constant. Well, what happens if one of those limits is infinite? If either or both of the limits of integration are infinite, then you have something called an improper integral. And with those, what we do is pretty simple, but you do have to show the work if it's a free response question on the AP exam, that if you've got f that's continuous on some interval from a to infinity, then if you have the limit, or if you have the integral from a to infinity of f of x dx, what we do is we come up with a variable. It doesn't matter what it is, except don't use x. But the limit is b goes to infinity of the integral from a to b of f of x dx. So you're actually doing a limit. And what we're going to say is that if this limit exists, that this improper integral is equal to whatever that value is. We say that this improper integral converges to this value. Likewise, if the lower limit is infinite, so it's negative infinity, we can do the same sort of thing. If the limit fails to exist in either of these cases, we say that the improper integral diverges. And that can, remember, fails to exist can be because it oscillates, it can be because it goes to infinity or negative infinity. There's all sorts of ways it can fail to exist. You can also have both limits be infinite. If that's the case, you must split it into two separate integrals. Where you split it does not matter. As a matter of simplicity, we almost always split it at 0. And people are like, was that because 0 is halfway between negative infinity and infinity? I'm like, well, there is no halfway between negative infinity and infinity, right? Because infinity is not actually a number. But for simplicity, for our mind's sake, we usually just split it at 0. So in this case, the original improper integral converges only if both of these converge. If one of them diverges or both of them diverges, then this whole thing diverges. Okay? So let's evaluate these integrals and state whether or not it diverges, or state that it diverges. So here on this first one, the integral from 1 to infinity of 1 over x dx, we need to first rewrite it as a limit. So I'll rewrite it as limit as b goes to infinity. And again, there's nothing magic about b. I usually use a for the lower limit and b for the upper limit. From 1 to b of 1 over x dx. And yes, I know this is kind of a pain, but you have to carry that limit the whole time. You can't just discard it and then come back to it. So this will be the limit as b goes to infinity of the natural log of x evaluated from 1 to b. So that'll be the limit as b goes to infinity of the natural log of b minus the natural log of 1. Well, that's infinity minus 0 is infinite. Therefore, the integral diverges. And what's happening here is if we look at the graph of y equals 1 over x, looks like this, and we're starting here at 1. Basically what's happening is, although that graph is getting smaller and smaller, it's not getting smaller fast enough. It turns out, and we'll save talking about this, I think, until another time, but if it was 1 over x squared, where the denominator was getting big faster, so the function was getting small faster, that improper integral actually converges. So it's all about how quickly it gets small, or the graph gets small, as to whether or not this is going to converge or diverge if you have a decreasing function like this. All right, let's look at a couple of other ones. The integral is from 1 to infinity of x e to the negative x. Well, that's going to be the limit as b goes to infinity of the integral from 1 to infinity of x e to the negative x dx. Now, how are we going to evaluate this particular integral? Which of our techniques of integration are we going to use there?
By parts.
Yeah, we've got to do it by parts. And so what I'm going to do to save myself from having to write nearly so much stuff, I'm going to come over here and do an indefinite integral for this until I have it in a closed form, and then I'll substitute in. Does that make sense? Let me show you what I'm talking about. So I'm just going to do, what's the integral of x e to the negative x dx? All right, so remember our limit, no logarithms, no inverses, but there is a polynomial, so we'll let that be u. Let u be equal to x, and dv be e to the negative x dx. Then du will simply be dx, and v will be the antiderivative of e to the negative x, which happens to be the same thing as the derivative of e to the negative x. It's negative e to the negative x. So I've got u times v, so I've got negative x e to the negative x, minus the integral of v du, so that's going to be plus e to the negative x dx. So that'll be negative x e to the negative x minus e to the negative x plus a constant. So back over here, we'll rewrite this as the limit as b goes to infinity of negative x e to the negative x minus e to the negative x, all evaluated from 1 to b. And see, what this will save you from having to do is having to write that limit over and over again while you're figuring out what the integral is going to do. That's the reason that I tend to do that. So then this will be the limit as b goes to infinity of negative b e to the negative b minus e to the negative b minus negative 1 e to the negative 1 minus e to the negative 1. It's probably helpful for you to rewrite this as the limit as b goes to infinity of, notice I have a negative and an e to the negative b, all that can be factored out of that. So this is going to be the opposite of, I'm going to put the e to the b in the denominator, and I'll have b plus 1 in the numerator, minus, let's see, these are actually both the same, aren't they? This is going to be negative 2 over e. Now, if you want to be super picky about it, I could say, well, you need to show me L'Hopital's rule on this. But at this point, I want you to, for these problems at least, be able to look at that and go, look, yes, the numerator and denominator are both going to infinity, but who's going to win? Yeah, e to the b is much mightier. So that's going to go to 0. So this whole thing goes to 2 over e. So therefore, the integral diverges to 2 over e. Or excuse me, converges to 2 over e. All right, now let's look at some where both limits of integration are infinite. So first we need to split that into two parts. And again, like I said, I almost always split it at 0. Unless there's some reason not to. So now we'll rewrite those as limits. So it'll be the limit as, for the lower limit, I almost always use a. So the limit as x approaches, as a approaches negative infinity, the integral from a to 0 of e to the x dx, plus the limit as b goes to infinity of the integral from 0 to b of e to the x dx. So that'll be the limit as a goes to negative infinity of, this will be e to the x from a to 0, plus the limit as b goes to infinity of e to the x from 0 to b. So this would be the limit as a goes to negative infinity of e to the 0, which is 1, minus e to the a, plus the limit as b goes to infinity of e to the b minus e to the 0, which is 1. For the first half, it looks like things are going to go all right. We've got 1 minus, as a goes to negative infinity, that's 1 over a to something really, really big, that goes to 0, plus, and this limit does not exist, right? Because as b goes to infinity, this goes to infinity. Now, be really careful. Don't write plus infinity minus 1 like it's a number. Okay? I don't know if you actually get dinged for that on the AP exam. It's just bad notation. So this part will say converges to 1, but this part diverges. Therefore, the integral diverges. And actually, if we even thought about that for just a second, if you look at the graph of e to the x, and you're doing the area underneath that curve, Over here, yeah, there's no problem. Over here, yeah, that's a lot of area. And it's just going to keep getting bigger and bigger. It's something that we would have guessed. This next one, you might not guess. So again, we need to split it. So we'll do the integral from negative infinity to 0 of dx over 1 plus x squared plus the integral from 0 to infinity of 1 over 1 plus x squared dx. And we'll rewrite those as limits. The limit as a goes to negative infinity of the integral from a to 0 of dx over 1 plus x squared plus the limit as b goes to infinity of the integral from 0 to b of dx over 1 plus x squared. So it'll be the limit as a goes to negative infinity of, what is our antiderivative here? Not quite. Arctangent, right? This is inverse tangent. So that's from a to 0 plus the limit as b goes to negative infinity. Actually, goes to infinity of arctangent of x from 0 to b. All right, so arctangent at 0 is 0 plus, well, let's think about the principal branch of tangent, which looks like this. Where this is at negative pi over 2, and this is at pi over 2. So as tangent goes to negative pi over 2 from the right-hand side, this goes to negative infinity. So this is, minus negative pi over 2 plus, as arctangent goes to infinity, or arctangent of x as x goes to infinity, that's going to be pi over 2 minus 0, and the whole thing ends up going to pi. It's one of those weird places where, I mean, if you just looked at this and didn't know it had some trig function associated with it, you're like looking at 1 over 1 plus x squared, which doesn't look like much of anything. It just kind of goes like this and like this. Turns out the area as you go infinitely to both ends approaches pi. That's just weird. All right, moving on to page 3. So the other thing that can happen that can make your integral improper is if somewhere between the two limits of integration, your function goes to either positive infinity or negative infinity. So if that happens, we're gonna break it up, and we're just gonna look at the limit as c approaches whatever that is from one side or the other. Let me show you. I think it's easier than reading this. I think reading it, my eyes start to cross on this. I think it's easier just to do an example. So like on this one, where is the problem in this one? Where does this function go to either positive infinity or negative infinity? 2. At 2, right? So, and 2 is part of my integrand. So what I'm going to do is I'm going to rewrite that as the limit as b goes to 2 from the left. Now, it's not always important that it's from the left or from the right. Sometimes it is, though. And the reason we're going from the left is we're starting at 1 and we're going towards 2. So we've got to be coming from the left of the integral from 1 to b of dx over x minus 2. So that's going to be the limit as b goes to 2 from the left of the natural log of the absolute value of x minus 2 evaluated from 1 to b. So that's going to be the limit as b goes to 2 from the left of the natural log of the absolute value of b minus 2 minus the natural log of 1. All right, so now we're stuck. The natural log of 1 is 0, so we're just stuck with this part. And we're like, okay, what does that do? So as b approaches 2 from the left, then b minus 2, that's going to be small. And if b is not quite 2, this is going to be negative, but it's going to be small negative numbers, right? But we take the absolute value of that, and that's going to get closer and closer to small positive numbers, right? Near 0. So you're like, okay, natural log of something that's near 0 but is still positive. Oh, well, that's negative infinity, isn't it? This diverges. And since that diverges, so does the integral. All right, where is the problem on our next one? Yeah, this has an infinite discontinuity at 2, right? So we're going to have to split this at 2 into 2 separate integrals and look at each part. So we're going to have the limit as b approaches 2 from the left of the integral from 0 to b of x minus 2 to the negative 2/3 power dx plus the limit as a approaches 2 from the right of the integral from a to 3 of x minus 2 to the negative 2/3 dx. So then this will be the limit as b goes to 2 from the left of, we'll add 1 to the power, that'll be to the 1/3 power, times the reciprocal is 3. So this will be 3 times x minus 2 to the 1/3 power from 0 to b plus the limit as a goes to 2 from the right of 3 times x minus 2 to the 1/3 power from a to 3. So substituting in, we have the limit as b goes to 2 from the left of 3 times b minus 2 to the 1/3 minus at 0 this will be 3 times negative 2 to the 1/3 power plus the limit as a goes to 2 from the right of, this is just going to be 3 because it's 3 times 1 to the 1/3 minus 3 times a minus 2 to the 1/3 power. All right, well, as b approaches 2, and it doesn't matter from the left or from the right, b minus 2 is going to approach 0, so that is going to all approach 0. So that's going to be negative 3 times the cube root of negative 2 plus 3. And then as a approaches 2 here, our negative 3 times a minus 2 to the 1/3 will also approach 0. So this is 3 minus 3 cube roots of negative 2. Whatever the heck that is. I have no idea what the cube root of 2 even begins to look like. Square root of 2, I know that one, and I don't know why. It just stuck with me. It's 1.414, approximately. All right. I'm going to show you this last one because it leads to something else, and they toss a couple of these in here. The problem is the integrand here doesn't work real well for us. It's like, well, how are you supposed to take the antiderivative of e to the negative x squared? And I wrote a note to myself because I sometimes forget this. What we're going to do is we're going to compare it to the same limits of integration, e to the negative x dx. Now, if you have e to the negative x squared, since the power is higher, and we have a negative exponent, the x squared is going to get big faster than x does, right? And it's negative to the negative power, so that means we're going to be raising e to higher powers over here, higher negative powers, than we are here. Okay? So this is always going to be less than or equal to the integral from 1 to infinity of e to the negative x dx. So what we're going to do is we're going to find out whether this new integral converges or diverges. If this one converges, and this one is smaller than that, it's got to converge also. Now, if my new one diverges, well, I have something smaller than something that diverges. It doesn't really tell me anything. So we're hopeful that this is going to converge. So we'll do the limit as b goes to infinity of the integral from 1 to b of e to the negative x dx, which will be the limit as b goes to infinity of negative e to the negative x from 1 to b. So it'll be the limit as b goes to infinity of negative e to the negative b minus negative 1 over e. As b goes to infinity, e to the negative b is going to go to 0. So I've got 0 plus 1 over e, so that's equal to 1 over e. So what we know now is that the integral from 1 to infinity of e to the negative x squared dx converges to something, I don't know what, less than 1 over e. And that's the best we can do. Not really satisfying, is it? Okay, that's it for today's lesson.